We have been talking about various issues in computer graphics, primarily modeling, rendering. Right? So today we are going to start another aspect which is also very important in computer graphics, which is animation. Right? So much of what we do through computer animation in fact has been inspired from conventional animation. Right? So if you just look at the term animation, right? So it has origin from a Greek word animos and Roman anima, right? Which basically means to bring to life, right? So there is a sense of evolution over time. Right? So things are changing over time. That's what we capture through animation. So conventional animation has been there for a long time, right? So, and the primary concern there of animation techniques has been to create this illusion of movement, right? So what are we trying to do is basically have the aspect of movement which could be just an illusion, right? Without simulating the motion in its physical sense. Right. So what it may involve is basically, let's say, creating photographs, a series of photographs, right, as frames, and then run through those frames over time. Okay, that is the idea behind what happens in conventional animation. So this aspect of illusion of life has been used by various commercial setups, even Disney animation, for their productions. Right? So for instance, if you look at what I am trying to show through this illusion of movement, so if you look at the example here, each of these images which you see here, right, they are in some sense a still photograph, okay, with different poses or different variations, okay, and if I run through all these frames over time, so if I just timestamp them, that this is the first frame, this is the second frame, this is the next frame, and so on, what I would obtain a sense of motion, right? And that's what we are saying, that is an illusion of movement, although each of the frame is actually a snapshot. Right? It's a static frame. Okay. So that's what happens in conventional animation, and that has been the practice since its beginning. So now we are also going to look at how we use computer in conventional animation. Right. So if you look at what we have observed, so animation refers to the process of dynamically generating a series of frames of a set of objects, right, or regions in a scene, right, where each frame is an alteration of the previous frame. Right. Now, if you look at the kind of restrictions it may impose, is that one, we are talking about a construction of a frame, which is a snapshot, right? So the notion of real-time animation is not there, right? Because you are generating a frame, and then you collect the series of frames and run over time. Okay, and the other thing is that it remains in 2 dimension, right? The kind of example we have seen. Okay, so now if you look at the process which is generally employed in the conventional animation, what do we have? We have a notion of what we call a storyboard. Okay, so the animator who is generating the sequence of animation basically creates these drawings, right, which are in a sense capturing what should be the frame, what are the contents in the frame, right, and how these contents are to be laid in that particular frame, right. So what you are trying to do is you give a pictorial depiction of the frame with the description you want to associate. Okay, that's what we mean by storyboard. Even today, this is an important step when we generate animation films. Okay. So now, then we have a notion of what we call as keyframes. Okay, so while we are generating these frames, it is perhaps not desirable that you do this for each frame. Okay, so what you have a notion of that there are certain keyframes in the sequence which require proper description, which require proper content definition, right, and then maybe the other frames would be computed using in-betweening of these keyframes. Okay, so that is the notion of keyframes. So you choose the important frames. Now in-betweening basically means that how do you get the frames which are between these keyframes which you have defined. Okay, so that in a way require a technique like interpolation, right. So you have defined these keyframes and then you may employ an interpolation to be able to compute the in-betweens. Okay. Now once you have done this, then there is a process of painting these frames which you have generated, the entire set of frames, right. So you are doing a sort of a redraw on a film, which could be using acetate cells. Okay, so basically film where we produce the final animation. Okay. Now one of the aspects which is very popular in the conventional animation is called as stretch and squash, right. So it is a very simple idea. Imagine there is a sack with partial flour in it, right, flour in it, and then what you are trying to do is squash and twist and deform that sack to be able to generate various effects. Okay, that's what is illustrated here in this, right. So this is a completely squashed, this is stretched, this is twisted. Okay, so all this is showing that you can actually generate various form and shapes using the technique of squash and stretch. Okay, so this even inspires for a technique which you might use when you are using computer animation. Okay, so this is one technique, and the one of the aspect which we observe in conventional animation, particularly in 2D cartoon animation, is this stretch and squash, right? Because what we are trying to do is have some caricature, right? The caricature in fact does exaggeration, right? So you want to exaggerate so that what you are trying to impress upon is believable. Okay, so the technique of stretch and squash and others are basically for doing this, for having an exaggeration. Okay, so you can straight away observe that this is some sort of a stretching of this, right? This is some sort of a squashing. Same idea, isn't it? So various expressions in animations can be generated using just the principle of stretch and squash. Right. Okay, so next thing is that let us try to sort of see the other aspects which we are trying to address in computer animation. Okay, so one thing, as I mentioned, that the conventional animation is primarily image by image animation. You generate every frame. Okay, So when we are doing image by image animation, there is a notion of you compute a frame, right? When you are using computer animation, you store that frame, right? And then you draw the frame when you need it. Okay, so this is the 3-step process which is involved in image by image animation. Whereas if I want to do a real-time animation, so real-time animation basically is a process employing compute the frame and draw it. So there is no notion of storing it. I compute it and draw it. Right? Now, one needs to look at the rate of display which you will require to use, right? So typically when I am generating an animation, I require, depending on what display standards I have, 30 frames per second or 25 frames per second. Okay, so this is just to enable that our visual perception doesn't perceive the discrepancies in the frames or jerks in the frames, the transitions in the frames, right? We just see a seamless sequence of frames, right? Now, if you look at some sort of a characteristics of animations, right, one can see there are 3 primary characteristics which may contribute towards animation, right? So for instance, I may have spatial characteristics, which basically is saying that there are things like position, orientation, shape, form, which is going to change, right? So that's what we mean by spatial characteristics of animation. Okay. Similarly, you also have temporal characteristics, right? So there could be a notion of velocity, there could be a notion of acceleration, right? It is just not that things change, but things change differently with time, right? Similarly, there could also be visual characteristics which contribute, right? So there could be change in color over time, there could be change in texture, and so on, right? So one can see these as a main 3 characteristics which participate towards contributing animation, right? So keeping these in mind, let's try to look at the techniques which could be used for animation and what has been used over time historically in computer animation. Okay, so one method which is the rotoscopy. So there are various methods and we try to look at in 4 categories these methods. One is rotoscopy, then keyframing, then we have parametric animation, and then algorithmic animation. So this basically covers a spectrum of various techniques which we may have for animation, right? So let's try to see each one of them in more details. Okay, so let's see what do we mean by rotoscopy. So rotoscopy basically implies that you are trying to record or register data for each frame, right? So when I say data, that means it may imply everything. It involves the geometric description of the scene, it involves the illumination characteristics of the scene, and so on. So everything is recorded. Recorded could also mean that I generate that, right? So I registered that from some means, right? I acquire them. So what we are looking at is an approach which is extremely data intensive, right? And if you look at this technique could be useful in particular when I am trying to capture a complex motion which I may not be able to generate by any other technique, right? And also when I am doing so, it is realistic because I am capturing every frame, right? But if you look at as an animation creativity, it's actually less creative since it's just brute force, right? The only emphasis is that you capture the data which is required for each frame, right? So we observe that this is in a sense a data driven animation. There are lots of data which need to be handled, and many techniques today you might have seen through motion capture could fall in this category, right? So this is one of the earliest technique where every frame was registered or recorded, but nowadays because of the complexity we want to include in the animation, this has again become popular, also because we have the acquisition methods, right? So there are lots of motion capturing ways and methods which we can use these days through sensors of various kinds, right, which can give us the required data, right? And also they are technically challenging because what you need there is the brute force data which is coming perhaps maybe at a much larger speed, right? So the amount of data you get could be noised, right? And what you need may be just a small set of that data, right? So you need to filter that data according to your application, right? So this has again become a sort of a trendy method of animation today. Okay. Now keyframing, as we were talking about what do we mean by keyframe. So the notion of keyframe is very similar to what was seen in conventional animation. Okay. So we have this selected or keyframes which are specified, and then we use some interpolation to compute the intermediate frames, right? And this approach is again, though simple, is very popular and still in use. Okay, so most of the animation softwares have keyframing. Okay, now one of the limitations which we may observe later is that it actually can cause inconsistency in the result, right, or can give you incorrect results. Okay, so let's see what do we mean by this. So if we just see the formulation of keyframing again, what do I have if I have a timeline here, time axis, which is nothing but in terms of the frames I specify these keyframes as, let's say, KF1, KF2 and KF3, right, and I compute the frames F1, F2, F3 and so on, which are in between these keyframes, right. So any frame Fi, which is the intermediate frame, which may be reflecting the position of a point or an object, then all we are saying is that this Pi, which is the position of a point or the object for the intermediate frame, is a linear interpolation of the position at P1 and the position at P2. Okay, so linear interpolation is one way of doing the interpolation of keyframes, right. Okay, so now let's see what are the consequences if I use linear interpolation. So if I have linear interpolation, one may have discontinuities, right, discontinuity in terms of the spatial discontinuity, or it could be temporal discontinuity. right? So in order to address the issue of discontinuity, you may use splines. So splines are basically ways of interpolating which are higher order interpolations, right, which can give you higher order continuity. Okay. Now if you look at examples here, so there could be some unrealistic results which we may obtain. So there is, let's say, an example where I define keyframes at kf1, kf2 and kf3, right? So it's something trying to simulate that some object or a ball is thrown up and it falls, right? Now if that is the situation I am trying to animate, right, if I use linear interpolation, this is going to give me a result like this, right? So these white circles are showing the intermediate positions, right? So what we observe is that this is not capturing the notion that when I throw a ball, right, it goes with certain acceleration or velocity and it reaches this point, right, it sort of slows down when it reaches the highest point and then again an acceleration starts, right? So nothing of that sort gets captured here, right? So when I see the resulting motion which I will get using this interpolation may not be realistic. Okay. Now similarly, so let's say there is an example of linear interpolation here. So here the interpolation I have from one frame to another frame, right? So these are sort of frames which are specified over time, okay, and all I have is a trajectory which is computed using linear interpolation where this object moves. Okay. Now there also if I use linear interpolation, it causes discontinuity, right? So wherever a joint is coming, I will see a discontinuity in the path and that would give me some jerky motion, right? So this, as I said, that could be corrected if I had used a spline curve, right? So if I had, let's say, used cubic curve interpolation, then I would see a smooth transition over this path, right? So the path is continuous. Okay. So this may be more realistic and would not have these jerks or the discontinuities. Okay, now again, as we are looking at the issues of interpolation, now one can incorporate, let's say I have used interpolation, but what I want to also capture the notion of that there is a slow start in the beginning and then there is a slow stop, right? So we call it that slow in, slow out. Okay, so what is happening is that if I use some function of this form, right, which is a function of a parameter t, which I am going to use for interpolation, would give me the impression of slow in, slow out, right? So I can use a function for my interpolation rather than just using a linear interpolation, right? So here this interpolation is basically on an attribute which could be a position, which could be anything, right, which is represented through Vs, and V is the attribute of the end frame, and I do the interpolation using this 1 minus Ft Vs times Ft instead of just using T, right? So now any other function, if I want to use, could be incorporated through FT. Right? So this was just to have slow in, slow out, but if you want to have some other kind of variation, then you can use that function. Fine. Now again, looking at the problem of interpolation, so some of these problems which we have looked at, which arise from interpolation, and in particular, let's say linear interpolation, we can resolve, right, either using splines or, as I said, these functions for interpolation. Now there is another issue here. Let's say when we are talking about interpolation, and particularly referring to the interpolation of shapes. Okay. Now let's say I have an object here for which I have a keyframe 1 at t is equal to 0. So this object is nothing but a square with vertices at 1, 2, 3, 4. Okay. And this is my another keyframe, let's say at t is equal to 1, kf2, which is again the points 1, 2, 3, 4 a square, right. So in a sense that this square has now transformed to this square, right. Now if I apply a simple interpolation technique which I use for keyframe and try to compute what happens to the shape at, let's say, t is equal to 0.5, what happens? A dot will come, right. So the whole shape is distorted, right. So that's what happens. Okay, this is what the result is. Now if you compute all the transitions, right, going from keyframe kf1 to keyframe kf2, it will pass through this, right, which would look strange. Okay, and one can actually observe these issues or these problems at many different situations, right. So now in fact if somebody observes that it's actually a rotation, right, then perhaps a different method is required to be able to generate again an intermediate frame here, and perhaps using only interpolation, right, but not employing or not using interpolation on the shape or the set of points. Right. So these things have to be kept in mind when you do keyframing. Right. This is what we mean by inconsistencies which can arise using keyframe animation. Okay. So an alternative is, which is actually inspired from what we have observed, is to use a parametric animation. Okay. What do we mean by parametric animation? See, if we look at many times in many situations, the animation is caused by a set of parameters. Okay. The shape change or the form change is a consequence in change of some parameters. Okay. So instead of doing the shape interpolation, you may use interpolation of that parameter. Okay, so your definition of the animation is in terms of that parameter, right. So a very obvious example is shown here. So for instance, what you are doing is you are doing some kind of a motion of an arm or a robo arm, right. So you have a robo which rotates from here to here, right. So when this happens, the entire motion can be parameterized by an angle of rotation, isn't it? Now I can generate animation using interpolation of this parameter. right? So the benefit is that it obviously requires less data because I am defining the animation in terms of this, right? I don't need to look at the entire shape. Okay, I have a shape somewhere, right? And the entire animation is then defined in terms of this parameter, which I apply onto this shape, right? So it's some sort of a transformation which I derive from this parameter and apply to the shape of the object, right? So that's what we mean by parametric animation. This is particularly relevant, as I gave you an example, motion of articulated structures, right? Now there is another category of animation which we refer to as algorithmic. Okay. See, many a times we observe certain laws of physics or motion to be the driving force for animation, right? So in fact what we are trying to do in animation is to simulate those situations, right, for which we know the law of physics or law of motion. Okay, then it is perhaps better to do or use that law of motion for creating an animation. Okay, so a very simple example is shown here. So let's say you have a motion of projectile. Okay, you throw some kind of an object from a height and it hits the ground. And that is the kind of thing you want to simulate. Now if you use a simple interpolation, then obviously you may get something like this, right, a dotted line which is shown here. So that is through a linear interpolation, which is completely wrong, knowing that it is a projectile motion. Okay. So whereas if I had used the law of motion, right, a simple equation to generate this motion, then I would have got this. So again, this is not a real simulated trajectory which I am showing here. This is some curve which I have drawn using tool of a PowerPoint, right? So, but this is just to indicate that I could compute or do the simulation of this entire projectile motion with the known equation of motion, right? So I can embed the law of physics or law of motion which is there in the process which I am trying to simulate. Okay. So this gives you the spectrum of technique which could possibly be used in computer animation, right? So let me just give you an example which will illustrate you some of the techniques which are used even in the commercial studios. Okay. So here is an example. Actually this is an example of you perhaps already know Monster Inc., right, by Pixar. So Pixar is a animation company. So this is a Pixar project with Disney, right? So they have produced this. So here what you see is that this in a sense gives you various stages which may be required for animation. Okay, so here for instance you see the first thing which you need to have is a sketch, right, which could be drawn by the animator, right, which is what gets used in the storyboard. Okay, so you try to give an expressive depiction of what is there in the frame or in that keyframe, right. Now correspondingly, well, this does not correspond to this frame though, but then the idea is that you try to do some color coding right, to reflect what are the different colors you may be using for these characters. And in case if you are just using 2D animation, right, then you assign the various colors which you would be using for portions here. Okay. Now, if you have the 3D animation, then you try to build the corresponding 3D models, right? Or you already have, let's say, 3D models, and you pose these 3D models according to your sketch, right? So 3D model basically here, for instance, are shown through the mesh models, wireframes. Okay, right. So this is a character called Sully, I believe, and this is Mike. Okay, so then this is what your rest of the scene is, the staging of the entire action, right? So this is the scene building, where you put whatever is required. So do the necessary modeling here. Okay. So, and then you have your illumination. Okay, so this was wireframe, remember? This was wireframe with the color scheme you might have defined. Now this is a shaded model, right, where you see the shaded objects onto the scene. Okay, and then you may also have further realism through addition like fur or any other aspect you want to attach. Okay. So all it is showing is that once you have done this 2D displays of these sketches which capture your storyboard, then you create the necessary environment in 3D, right, and do the animation in 3D. Okay. So let us see the animation here.
I can't believe it.
Oh, Mike.
I was on TV. God, did you see me? I'm on Metro. Hello? I know. Hey, wasn't I great? Did the whole family see it? It's your mom. What can I say? The camera loves me.
Okay, so there is also some task related to, you have created the visuals, right? Then you have to overlay the audio on it, right? So where you do the production, so there are set of frames which you have created, and then you have to overlay the sound on it. Okay, and then since it could be a longer sequence, right? So a typical computer generated film may have thousands of frames, right? So you may need to have necessary infrastructure to be able to compute those frames and store them. Okay, because typically these animation sequences are not real time. Okay, they are more in the sense of frame by frame philosophy. Okay, so next time we are going to look at more in details about some of the animation techniques, right? But this gives you an overview as to what are the various aspects in computer animation. Okay, thank you.